Hello, everyone. My name is Taqi Abrar, and I'm from Center for Advanced Robotics at Queen Mary, University of London. Today, we are going to present the interesting work we did in our lab. But before this, let me introduce you with my team: Daniel Khalil, Ahmad Hassan, Tayyib Ansari. And this lab is managed by Professor Kasper Altufa. And what we are going to do is we're going to show you a few interesting robots and interesting things that uh, are very useful.
Okay, so the first robot we're going to show you is a eversion robot. This robot is a robot that can grow in length, and it does this through pneumatic pressure. This robot can be made from fabric or can be made from plastic sheeting. As the air goes into the robot extends in length and grows. This is its way of actuating itself and its way of moving. And in doing so, it can move through tight and narrow constrictions in its environment. As you can see, this robot is bending. Its method of bending is through a pouch mechanism system. So the pouches are like pockets, which we can fill with air, and they can contract. So if you have pouches on the left-hand side, for example, and you fill the pouches with air, they contract, and that allows the robot to bend in the desired direction. So the robot that we showed you was applied to going under buildings, going under the buildings to inspect their foundations. But we also develop robots that are able to operate underwater, for example, in coral reefs, oil platforms and oil rigs, and wind turbines and that kind of infrastructure as well, and also shipwrecks. The special nature of eversion robots allows us to do this because of its non-destructive method of moving. So as you can see, we have an eversion robot in the tank. This one is also a fabric eversion robot. And what we're going to do is we're going to show you growing in length. So as we pump water inside instead of air this time, you can see the robot extending in length. And it's able to grow through the underwater environment in a non-destructive manner. So as you can see, we've shown two robots made out of eversion robots made out of fabric and two eversion robots made out of plastic. This robot is made out of a polythene plastic. So as you can see, these robots can be made from a variety of different materials and can be constructed from very cheaply. So the next robot that we're going to discuss with you and show you is our robot gripper.
So you can see this gripper, and it's made from fabric, and it's again very lightweight and low cost, and use only air to for work. And here you can see a small demonstration of this gripper grasping a bottle, and with very low air pressure, it can work. It can hold different objects. It can grasp, and the thing is, it's very lightweight, flexible, so it won't harm or destroy anything. It's very safe. But the main idea of all these prototypes we have shown you, like eversion robot underwater, in the air, on the ground, and this now eversion based gripper, the aim is actually to use and construct a robot that is useful for human, that can work with human. So the final aim and the main prototype, or the main aim end goal, is to make something like this. There's a small prototype of a prosthetic hand that we are going to use, and the aim is to make it from fabric and use pneumatics to work on it. So you can see that it is a very small gripper, and it's very small, and you can see it is very flexible as well. And the idea is to use these materials and to construct something that is very helpful for human, and make a prosthetic arm from fabric that use pneumatics to work. And you can see this is a small finger working, and that's how, so use all these technologies that we have shown you to come to this end goal and make a small prosthetic hand like this. It is made by one of our colleague, Jan Fras. So to make something like this that can be very helpful for the human, and that can work with the human, because the gripper that are commonly available either are made from rigid materials, or that are heavy or bulky, which is not safe for human robot interaction. So made something from the technology that we previously show you to come to this end goal. And And that's all from our side. And if you have any question, it says, what do you do if the growing robot gets a puncture? Very interesting question. And the thing of the advantage actually of eversion based robot is, even if they got punctured, they work, because the air pushes the the material which is inside, and the robot grows. Even with a puncture, these robot grow, and they perform the work they are meant to do. Even but the efficiency can be low and decrease, but they are capable of doing work even they are punctured. A small puncture cannot affect the robot's task, and the robot can perform the task that is given to the robot, and it can even grow with a puncture as well. And we have tested this in our labs and outside the lab as well. Like, even with a puncture, a small puncture, the robot grows and grows, and it can bend and grow again.
So even if it has a puncture, some people in academia use the puncture to an advantage. So if they don't have a pressure regulator, which we are very fortunate to have and afford, so they what they do is, instead of having a pressure regulator, they have like a small hole in their version robot, so they're still able to extend and grow their version robot, um, with a puncture, and the puncture regulates the amount of air that's going flowing through the robot. And they can control the extension by the punctures in the robot surface. So a puncture is not always a bad thing. If you want to reduce the amount of force the robot generates, a puncture might actually be beneficial to you.
Okay, so we have a question about shape memory and implementing it on the robot. Yes, we can. There is no doubt we cannot implement. Yes, we can implement, but the thing is the response time. So, as we you can see in the videos of the Eversion robot, the response time of our robot with the pneumatic is very high, and it's very quick in response. But with the shape memories technique, the response time is very low, because it takes time to change its states. So because of this, we move from shape memory to uh, pneumatics, and it's more, the time response is very quick. And again, the safety, because what we want is to use it with the human, and we don't want anything that is thermal or electric to be integrated with the human. Even though there can safety measures can be taken, but we want it to be very very safe. And for this, we are using pneumatics. So you can see, if there is all around us. So and the thing is, the pressure we are using are less than 1 bar. It's very low pressure that we are using to operate our devices. So we are making them very soft, and not very complex mechanism we are using in our robots. So if we try to teach about our robot to the people, so they can understand, like air and everything. So we supply the air and it grows, and it's very very simple techniques we are using to operate our robots. But yes, we can implement several other techniques, including shape memory, and even motorized system and tendons, where we pull the tendons or rope and it can bend. We can implement, but there are difficulties and safety concerns, and not only safety, but there are also challenges as well. So with the pneumatics, we overcome all these challenges and safety concerns. To That's why we use pneumatics. So there's only one system for the whole robot, and you can see we showed you several prototypes: eversion robot on the ground, eversion robot in the air, eversion robot inside the under the water, eversion based gripper, and prosthetics, and all using same pneumatics. And you can clearly see, like how simple pneumatics is, and how easily can pneumatics can be implemented on different robots, and it can be used in several applications. And our the link of our research group is in the chat. You can always contact us. And we are students from Queen Mary University of London. Our lab is Center for Advanced Robotics at Queen Mary, ERQ. And thank you for your time. And if you have any question, you can always come back to us. and the link of our lab is in the chat. Thank you. Thank you.
Thank you. Bye.
Bye.